The goal of building a spaceship is not only to take someone somewhere distant, but to make the inside of that craft as much like home as possible. This requires food, water, breathable air, enough space to move around, somewhere relatively comfortable to sleep, and hopefully another person or link to the world they left behind. As we peered deeper into the cosmos, we began to run into a major problem. Every space-based destination we wanted to visit besides our own moon would take months, if not many years, of coasting to reach, let alone the hundreds or thousands of years it would take to reach another star. But we may have missed an easy solution, one that we are standing on now. A ship more perfect than anything we could ever hope to build, and one we have been copying with every ship we've sent to the void. If we can't build a spaceship with enough of what we need from our own planet, why not just take the whole planet? Welcome back to Serious Science, and these are some of the best and most impressive of any ships humanity could construct. I meant what I said when I called our own planet a spaceship, and one we are desperately trying to copy, if not in far smaller capacities. Our world has abundant oxygen, food enough to feed billions of different species, and enough space to live quite comfortably. It soars through the galaxy, covering new ground every second of every day, and has traveled past uncountable stars during its lifetime. It is the perfect spaceship, hosting about 110 billion astronauts during its about 4.6 billion years of service, and has orbited the entirety of our galaxy 18 times since it was first launched. Before I discuss why taking an entire planet somewhere distant would be more desirable than just sending a specialized rocket, I want to list off just how many things we would need to take with us in order to survive in space. And it's more than you think. Food, water, and air are obvious, as these are the most basic things humans need to survive. We will also need gravity, as the bodies of those who spend extended periods in space without it show rather frightening amounts of bone and muscle loss, weakened hearts, and atrophied eyeballs. Living in space also carries with it perhaps the most dangerous of all effects, radiation exposure. As a matter of fact, there is currently a 6-month limit for people living in space before they absorb more radiation than they would living their entire lives on Earth. Creating artificial gravity through large spinning modules has been proven to be a viable option for long-duration space flights, and we can armor our ships against the radioactivity of space, albeit needing a lot more mass to accomplish this, which means higher costs for building and launching your ships. People also need other people, as if we sent a single person to even the closest planet, that being Mars, their nearly 2-year voyage would return them quite insane, or not at all. This means that we will need to exponentially increase the amount of life-sustaining supplies per person as we add more crew, making our ships even larger and more expensive to manufacture. But we are also surrounded by something that facilitates life as we know it that is rarely discussed when planning missions to other worlds: bacteria. The first of all life and the most evolutionarily advanced. Billions of them aid in our digestion, immune systems, and even hormonal balancing. Our bodies are as much of a spaceship to these creatures as our planet is to us, and we will need to take many thousands of different types of bacteria with us to other worlds if we want to keep our bodies and minds working at peak capacity. There is another thing our planet produces that has become noticeably absent in space by several astronauts who have returned, something whose effect or lack thereof has just recently become a focus of study. The sound of our own planet, not the sounds of nature, though this may too be desirable aboard distant crafts, but the infrasonic thrum of our tectonically active world. Our planet produces extremely low-frequency sounds as its interior churns, not loud enough or of a high enough pitch to be recognizable, but one whose absence can and has been detected by those who have left our atmosphere. The long-term effects of being disconnected to this ever-present soundscape still remains in mystery, as well as just how important this sound may be to our stability. If it is vital in a still unknown manner, it may be artificially generated on long-term spaceflights, or if it is a lesser adaptation that can be made, it may go unreplaced. But this seemingly benign lack of a certain infrasonic sound reveals just how many factors, known or not, may degrade our astronauts and colonists' minds during their long journeys. If we want to take ourselves to other worlds, we must keep in mind just how much of that world will need to come with us, both to continue our physical and mental well-beings. As we look around to what we cannot live without, our cargo spaces increase drastically, meaning that the only kinds of spaceships that can both reach other stars as well as keep a large crew healthy and alive during those many hundreds of years of travel will be ones of a necessarily gigantic size, many miles long, hosting spinning interiors that could be mistaken for the surface of Earth, if not a bit curved in the other direction. We need as much of our planet as possible just to survive, let alone reach other places in the universe. But I can already hear a multitude of voices asking me to address the rather large elephant in the room. Just how in the ever-loving heck, excuse the language, could we ever pilot an entire planet around like a spaceship? Surely you aren't thinking of covering half our world in loud, searingly hot, city-sized engines. They would probably blow our atmosphere off before they even pushed us outside of our solar system. Well, first off, I don't exactly have the bankroll of Jeff Bezos, so I won't be doing something like that anytime soon. Plus, mounting engines large enough to push our planet around would be an incredibly bad idea. It would be the greatest single feat of engineering ever undertaken by mankind, and would use up oceans worth of fuel just to push our orbit past Jupiter. They would also expel gargantuan amounts of heat, turning our atmosphere into a roiling oven, and would be loud enough to shatter the eardrums of every human on the planet, even those on the opposite side. If we wanted to take Earth with us, we will need something different. Something that doesn't endanger or directly influence the surface of our world. As it turns out, there is another kind of engine we could use that operates entirely without even touching the planet we would want to move. Gravity tractors. Our world is incredibly unique in almost every conceivable manner, one of which is the particularly gigantic moon our world has captured. The moon may orbit the Earth, but this circular dance is anything but centrally stable. The mass of our moon is enough to cause our planet to wobble widely around a singular point, not at the center of the planet, but higher up in the crust on the side facing the moon. As our moon orbits, it pulls the planet around this spot, the barycenter of our dual orbits. The moon exerts truly immense gravitational forces across our planet, capable of moving the oceans themselves and lifting entire ice fields as it passes overhead. Our interstellar engine already exists, and has done so before life began under its ashen gaze. If we can move the moon around in strategic bursts of direction, its gravity will pull our planet in that direction, creating what is known as a gravity tractor, essentially causing the Earth to fall towards the moon as we move it away just as quickly, towing our planet behind. But now I've simply moved the problem of propelling a planet down the line from our Earth to the moon. How would we move the moon around? Well, the moon is already an incredibly hostile place, one that would suffer little from the introduction of either gigantic engines or the detonation of strategically timed nuclear weapons across its surface. As these engines or detonations provide a downwards force to the moon, it will sway in its orbit, moving the Earth accordingly. If we were to detonate a salvo of warheads once the moon was facing the direction we wanted to travel in, then wait for the moon to circle back around to the opposite side of our planet, we could then detonate another set of explosives, stabilizing its orbit. If this stabilization force was not applied, our shifting of the moon's orbit would certainly move our own world, but would be likely to destabilize our moon into a disastrous inward spiraling orbit that would decimate Earth before we could take it anywhere useful. This continuous bombarding of the moon would indeed begin to move the Earth in the direction we wished, but would take immense time spans to make any amount of progress, perhaps even millions of years. A far cry from the hundreds or thousands a smaller artificial spaceship would need. And if something like this seems like a gargantuan undertaking for all of mankind, please consider subscribing, as I talk about these kinds of things all the time, going into the details of doing so. Back to the video. So can we do better than a gravity tractor? Absolutely, but it may require us to turn to another kind of planet as our potential starship. Earth is big, like truly difficult to comprehend big, with the only people who have ever been so far above it to see most of its surface being able to understand just how large of a planet Earth truly is. Our immense size actually slightly hinders spaceflight, with our powerful gravitational sink requiring rockets the size of skyscrapers to even get into a low orbit, and needing to push inefficiently through a smotheringly dense atmosphere. It is the largest rocky planet in the solar system, requiring the combining of all other rocky worlds and asteroids around us to even begin rivaling its size. In addition to how large it is, humanity can only ever occupy less than 30% of its surface, as the rest is covered by deep and tumultuous oceans. Of the 30% that is land, only about 10% of it has been colonized by humans, the rest being uninhabitable deserts and tundra, or simply land that has yet to become developed. We occupy so little of our planet's vast amounts of available land that if every human alive were to cram themselves together, it would create a shape not 0.47 cubic kilometers in scale. Quite a small mass, but by no means a comfortable one. If we truly wanted to create a spaceship planet capable of carrying a large crew of colonists, let alone the entirety of humanity, we can turn to worlds far smaller than Earth that could be moved around far easier. Our moon is still too large a body than would be needed to accomplish this task, and its removal from our orbit would seriously harm not only our own orbit, but of all of the processes and life that depends on the moon's effects to live. Our Moon-Earth system will need to be a package deal, both for those seeking to move them around and the biosphere that has depended on the existence of both for life on Earth to be possible. Gravitational attraction works on a logarithmic scale, meaning that if you were to travel 2 units of distance away from an object, you would experience a gravitational pull 4 times lesser. If we are planning to create ships large enough to mimic entire worlds, we will need to keep this scale in mind. If we build too large, we would not only become too heavy to move around efficiently, but would be crushed by our own weight, even using the strongest and most expensive materials. One proposed solution to supporting ultra-massive constructions are known as active support systems. They consist of gigantic load-bearing hollow pillars through which a magnetically accelerated liquid is rapidly pumped in a loop. The easiest way to picture how flowing liquid could make a system stronger is to picture a hose. Without water flowing through it, the hose becomes limp and easy to buckle. But once water flows through it at a high enough rate, even bending the hose in half becomes difficult. If we were to use heavy and uncompressible fluids in this active support pillar, they may become stronger than any material we could ever hope to smelt or manufacture. If we can use these Atlas pillars in constructing worlds, we could create structures of truly Goliath size, housing billions in a space that would have otherwise been filled with solid rock. We can save a lot of space when it comes to planets, as all but the surface is filled with useless mass and wasted living space. If we were to begin the transformation of a world that needed to house as many humans as possible, a smaller dwarf planet would be more than enough space, still leaving in as much natural preserves, man-made oceans, and available real estate as we are used to on our unmodified planet, all housed in honeycomb layers throughout the interior. Most of the dwarf planets we are surrounded by would be already far more space than we would need for such a task, leaving plenty of collectible rock and metal for future expansions of the core cities. I actually discussed the dismantling of such planets in a past video, which you can watch here. These artificial dwarfs could be perfected further, through the construction of custom worlds made from scratch. Now we stray farther from the moving around of Earth to a more Death Star-sized spacecraft, making maneuvering, departure, and arrival all far easier to achieve. If we think that hollowing out a planet may be too great an expenditure in order to produce a massive spaceship, we may simply begin from the ground up, ironically absorbing a few large asteroids for the required materials. The designs of such crafts may vary for the tasks they are envisioned for, but mimicking nature may provide certain benefits for survival in the void. With the size needed not only to house billions comfortably, and the creatures and systems we will need to bring with us to survive, but also the fuel and engines to move a ship, we may want to keep a spherical shape, one that keeps its integrity under its own pressures. We may also want to coat the surface in a thin layer of rock, which will protect from asteroid impacts as well as radiation. We may even want to produce an artificial magnetic field if we wanted to build structures on the surface. Though these ships would be massive, they would still be unable to hold an atmosphere, as only the largest of rocky worlds can do so. Our surface structures will need to be enclosed and armored. But if we do not use gravity tractors to move such worlds, how would we do so? While gigantic engines seem the obvious solution, we may be able to do better in both thrust and efficiency. If we are traveling with large amounts of gases as cargo, they could be ejected through pressurized tubes, blasting out into the vacuum. We may even coat large amounts of the planet's surface in reflective foils, creating gigantic mirrors for powerful solar lasers to blast and impart thrust through. Any solution we propose for moving such massive ships will need to fire for long periods of time, even hundreds of years, and will take a very long time to move that ship anywhere. Such is the trade between smaller, more fragile ships and one as secure as a planet. But how would we park around a distant world, and what would these ships do once they arrived? Well, if we used a combination of solar laser mirrors for leaving the solar system, we could store up enough fuel for onboard engines to use in slowing the ship back down, meaning we will need half as much spaceship in order to make the journey. These engines may begin to slow the ship down many decades before they had even entered the alien star system, requiring a long time to decrease the planet's immense speed. Once the ship had slowed to the point that it was now orbiting the target star, it could coast around the solar system, possibly using other orbiting planets and gravity assists, in order to slow their speed even further. catapulting them into a position where slowing to an orbit around our destination planet would be far easier. But what benefits would having a spaceship the size and shape of a planet be as opposed to a more conventional and smaller ship or fleet of ships? The largest benefit would be gained during the trip, as it would be much easier to sustain gravity, self-contained life support systems, and heavy shielding aboard something the size of a small moon compared to a spaceship that needs to save mass and space wherever possible. But once the journey is complete, what benefits do MoonShips have for the actual colonizing or exploration stages? If the goal was to turn the new planet into a human inhabitable world, our ships will need to be as big as possible in order to carry either the necessary materials to do so or the collection and refining systems to do the same. If our MoonShips are large enough, we could even use their new gravitational effects on the proposed planet to slow or accelerate its rate of spin, creating more Earth-like days or stabilizing an eccentric orbit. It could also act as a new artificial moon to stir up oceans, creating uniformity and ideal conditions for life, both introduced and naturally occurring. It would also serve as a spacious and home-like space station for colonists to live on while the planet below is undergoing terraformation. There is a common misconception that terraforming would be a gradual change that the colonists could exist within, as the atmosphere around them thickens until they can simply take off their helmets and start building colonial-style houses and Walmarts. In reality, you may want to be even further away than orbiting the world as it changes. This is because the amounts of energy, materials, and new chemistry reactions taking place on the world as we change it would be more catastrophic than can be imagined. This is because changing the conditions of something as large as a planet takes energy. So much energy that if it were released all at once, it would blast the planet into millions of molten chunks. You wouldn't want to be anywhere near the surface of a planet as terraformation occurs, as the surface may be undergoing intense molten reconstruction in order to either trap or release select elements. Plus, terraformation isn't going to occur overnight, or even within a lifetime. These processes, as they are currently understood, will take hundreds or thousands of years to complete, so a home away from home orbiting an under construction home will be vital. Size will be crucial in maintaining multiple healthy human generations awaiting the completion of a new world, and nothing beats a ship the size of a planet to get the job done. But what if we needed something more? Something a bit larger than just one planet. Suppose we wanted to send a few million colonists outside of our galaxy, a trip that will take many hundreds of millions if not billions of years traveling slower than the speed of light. They will need a planet's worth of living space, available resources to expand as their population does, and a source of energy that must output for billions of years consistently. What kind of moonship would be needed? There is another kind of astral body that would accomplish all of these criteria, one that could also carry with it thousands of either man-made or naturally occurring spaceships to the destination: a star. With how we currently understand astrophysics, if you were to move a star gradually, it would pull all of the orbiting bodies around it along with the added force, essentially dragging a whole star system with it. If we could move our own sun, or another smaller alien sun with multiple inhabited worlds orbiting it, we would be taking the entirety of all known and currently explored space along with us on our journey to another galaxy. Moving an entire star around like a spaceship may actually be far simpler than moving the planet, as there will be little in the way of decimating possible population areas or polluting the surface of a star with oven-like heat conditions. We won't have to balance thrust with how impactful those sudden changes in momentum will be to a ball of molten rock that can shift and split, destroying the thing you just spent hundreds of years building thrusters and honeycomb living quarters on. A star is already a gaseous, viscous ball of sheer energy and heat that can flow and distort, and is one of the last places we would be sizing up to start building surface structures on. It is also one of the best long-term reactors in the known universe, capable of releasing massive amounts of energy for many billions and even trillions of years in the case of smaller stars. Our own sun is surprisingly large and stable compared to most of the other kinds in the universe, so choosing a far smaller and longer living sun that already has a large amount and diversity of planet types orbiting it may be smarter than changing the position of Sol and Holy Terra. But what kinds of rocket engines could move something like a star that is made up of non-solid gas? One possible proposition is something called a Kaplan thruster, or two engines packaged as one. It is a double-pronged megastructure that would closely orbit a star. It would use either artificial magnetic fields or the existing ones generated in the photosphere, and use these to suck up ludicrous amounts of hydrogen and helium from the star. These elements would be separated between two fusion reactors, with the helium being accelerated outwards behind the star, and the hydrogen being focused down onto the star's surface. This would not only push the thruster towards the star, but would also push the star away before the thruster could collide, freezing the two equidistant from each other as the star accelerated. Another possible solution would be using the matter and light a star already shoots off in all directions for thrust. This would be done by constructing a gigantic curved mirror partially around half of the star. This mirror would focus all of the star's light in just one direction, and as we have seen with the light sail experiments on smaller ships, light exerts a push on objects it strikes. This would essentially turn the sun into one massive focused flashlight of thrust. These engines will need to fire downwards on the stellar orbital plane. As if it were aimed anywhere close to where our planets orbit, they would be gradually boiled away as the sun engine fired. When it comes to what we will need to become an interstellar civilization, bigger is not only better, but one of the only options we have to withstand the dangers and timescales of traveling such distances. And if we want to exist within and create Earth-like conditions on other places than home, what's better than just taking as much of home with us as possible? Thank you all so much for watching, and don't forget to cast your vote for the next topic under the Community tab.